Hey folks, this is lecture 9.4, the last lecture of chapter 9. So we're looking at buffers. This whole chapter, we've been looking at acids and bases, and one of the common themes throughout this entire chapter has been this slide and this idea of physiologic pH of blood, acidosis, alkalosis, if pH gets too low or too high, and of course death if it goes beyond that range. And so, our blood pH is maintained at a fairly narrow window of pH. And the question now is, how is this narrow range of pH maintained? And the answer is buffers. Okay, so that's what this whole section is about. And what is a buffer? Not this, nor this. Well, yes, but not in this context. A buffer is, in chemistry, a mixture of a weak acid and its conjugate base in approximately equal proportions. But a buffer is a solution that resists changes in pH when small amounts of acid or base are added. Right, and it looks like this in the green box. This is how acid-base homeostasis works to prevent acidosis or alkalosis from occurring. Okay, so the components of a buffer are a weak acid and its conjugate base in similar concentrations. Okay, they don't have to be the same, but order of magnitude similar, not like one is 100 times more than the other. They're about the same. Okay. Now remember what a weak acid and conjugate base are. Right? They're like a pair. They come together. A weak acid would be something like HA in general, and its conjugate base would be A minus. And so the difference between them is an H plus moving back and forth, right? And so a buffer has both of these in similar concentrations. The pH range at which a buffer works, or at which it maintains fairly constant pH, depends on the identity of the weak acid, and the buffer capacity, like how much acid can it resist, depends on the concentration of the buffer components. Right? Remember that we said it can resist changes when small amounts of acids or bases are added. So that has to do with the capacity, like how much can be resisted. So a weak acid and its conjugate base. Here are some common buffer systems. That's what we call them. This is actually a shot from the previous edition of your textbook where it was table 9.9. I believe it's table 9.5 now in your textbook, but it's basically the same table. So notice that the system name often it has both the acid and the base name. So acetic acid would be right here, and acetate is the polyatomic ion that no longer has the H plus, and it is the conjugate base of acetic acid. That's used commonly in laboratories to maintain pH. That one is, I believe, around 4.7. Carbonic acid, hydrogen carbonate buffer system is used biologically as in the extracellular fluid. Phosphate, H3PO4 and H2PO4 minus, that should just be a minus one there. Yeah, is intracellular buffer fluid. And then hemoglobin is also a buffer system, which the red blood cells use. Okay, so really, right, the big key here is that it's a weak acid and it's conjugate base. And we know the difference between these is an H+. With that in mind, here's your first check question. Which pair is not a buffer? Okay, which pair is not a buffer? Well, here's the thing about all these, right? They are all conjugate pairs. But there's one that stands out that's not a weak acid, right? And so this one is not a buffer. Strong acids cannot be buffers because its conjugate base is just an ion. It's not actually a base. All the rest of these are really nice buffers. So these three we just saw on the previous slide, and then this would be an ammonia buffer. All right, so let's look at some chemical equations and figure out how this buffer works and why it's resistant to change. So we have a buffer, let's say, of a weak acid, HA, and its conjugate base, A-. So we know we have, we can write a chemical equation for the acid when it is in water, right? Hydronium and conjugate base. But here's the important part, it is a equilibrium, right? So the base itself can combine or react with hydronium to return the acid and water, right? So now let's say we have this in approximately similar concentrations of these two. What happens if we add acid? So adding an acid means adding H3O plus, or H plus for short. And then we have an equilibrium. We simply think about the Chatelier's principle. What happens if you add more of this? Equilibrium shifts this way, producing more HA and H2O. So that causes a shift to the left, right? consuming most of the H plus that you just added. Therefore, H3O plus only changes very little. And remember, pH is dependent on H3O plus concentration, right? So all this is to say, if you add acid, H3O plus, it will basically get used up and turned into HA. And thus, pH does not change very much. So if we add a base, what happens? Well, don't forget that we also have this reaction going on at all times, the autoionization of water, and it's in equilibrium, right? So this product is equal to a constant, Kw. If OH increases, then H3O must decrease. If H3O goes down, equilibrium shifts to replace it, right? And thus, it doesn't change very much, right? So as it's kind of drawn out by the base, by OH minus, it's replaced by the weak acid turning into hydronium and conjugate base. So again, whatever you do, the system, because both of them are there, can fluctuate around that equilibrium. The Chatelier's principle comes into play, balance is found, and we have a very small change in H plus leads to a small change in pH. Here's another another way of looking at it. I kind of like this this plot down here. So here's like our initial buffer. We have equal quantities of the acid and the base. And then if we add a little bit of H+, right, that's going to combine with some of the acetate, and we'll end up with a little bit more HA and a little bit less A-, but it will basically consume all of the H+ that was added. And it's showing the same thing here in terms of reactions. And it says adding H+ will be neutralized by the weak base that is present and will produce acetic acid, which is what we already have in solution. And so it's resistant to change. Okay, that was adding acid, looking at like the amounts of things. Now if we add base, right, then the amount of HA goes down slightly, the amount of A- base goes up slightly, but the OH is essentially consumed and there's no change. So again, if base is added, the HA that is present will neutralize it to make its conjugate base and water. And its conjugate base is already there to some extent, and so it doesn't really have much of an impact. All right, let's look at an example. I think this would be the best thing to do next. All right, here's the acetic acid acetate ion buffer. It has a buffer range from about 3.8 to 5.8. And so it would be if you had acetic acid and let's say sodium acetate combined in equal numbers of moles. And here is the chemical reaction, right? HA plus water makes H3O plus and A minus. If we add acid to this buffer, right, all of these chemical species are there at equilibrium, but if we add H3O, it's going to shift the equilibrium to the left to minimize the amount of H3O plus. We'll look at adding base. And again, you have to think about OH minus and its relationship to H3O plus first, that if you add OH minus, it's going to be equivalent to removing H3O, which will cause a shift to replace it, and thus the pH won't change very much. All right, how about a check question? How does the addition of hydroxide ion affect the equilibrium of the buffer system shown here? Okay, pause it and answer for yourself. Great. Well, now notice hydroxide is not actually a part of this reaction, but it does have an impact on one of the parts of the reaction, right? If we add OH minus, that's like decreasing H3O plus. If you want to remember this equation, so if OH minus gets bigger, H3O plus gets smaller, which will cause a shift to replace it that way. Yes, so equilibrium shifts to the right. All right, so I think we'll stop here for part one, and we'll come back and focus on the carbonic acid hydrogen carbonate buffer in blood, probably for the rest of the time. But a quick review, right? A buffer is a solution that's resistant to pH changes when acid or base are added. It's made by similar concentrations of a weak acid and its conjugate base. And it works by equilibrium and Le Chatelier's principle to reduce the impact of H3O plus or OH minus added to the solution.